A sealed cooling system is designed to cycle the refrigerant from liquid to gas and then back to liquid again indefinitely. It does this using pressure and heat. 4 primary components make up a sealed cooling system: an evaporator, a compressor, a condenser, and a capillary tube. The component that absorbs heat from the air is the evaporator. It's placed in the freezer, where the greatest amount of cooling is required. The evaporator is simply a long, narrow tube compacted into an efficient size. Refrigerant enters this tube as it changes phase from a warm liquid to a cold gas at around -20 degrees Fahrenheit. As it travels through the tubing, it absorbs heat from the air flowing over it. The air becomes cold, and the refrigerant becomes warm. By the time it leaves the evaporator at the other end of the tube, it is around room temperature and can absorb no more heat. But the air that flowed over the evaporator is now very cold and can be distributed throughout the refrigerator. The refrigerant, on the other hand, is of no use unless it can be converted back to a liquid so that it can change phase to a gas again, absorbing more heat. To convert it back to a liquid, we must either lower its temperature below its boiling point or raise its boiling point above its temperature. Since we can't lower its temperature all the way to -20, we temporarily raise its boiling point by increasing the pressure. The refrigerant is drawn from the low-pressure evaporator into the compressor. The compressor takes this low-pressure warm gas and moves it to the condenser. The condenser is also a long tube compacted for efficiency, but it's much smaller than and cannot hold as much refrigerant as the evaporator. As the compressor continues to force refrigerant into the smaller condenser, the refrigerant compresses into a very hot gas. Compressing the refrigerant raises its boiling point well above the current room temperature, but it also increases the total temperature, so it is still in a gas state. As hot refrigerant travels through the condenser tubing, the cooler room temperature air around it absorbs some of the heat from it. Refrigerant exits the condenser still warm. We use that to our advantage and run a loop around the cabinet opening, where it will gently warm the surface, preventing any moisture and mold buildup. By the time the high-pressure gas reaches the end of the post-loop condenser, it has cooled to approximately 100 degrees Fahrenheit, passing below the new boiling point that we created, and thus changing from a gas back to a liquid. We are now ready to drop its boiling point back down below the temperature so that it will boil again, changing phase from a liquid to gas, absorbing heat. A tiny capillary tube is placed between the condenser and the evaporator that controls the drop in pressure. The size and length of the cap tube are carefully calculated to restrict flow at a rate that keeps the pressure high in the condenser and very low in the evaporator. When refrigerant leaves the capillary tube and enters the much larger evaporator tube, the drop in pressure instantly lowers the boiling point and the temperature back to its original point. The refrigerant immediately begins changing phase from liquid to gas, absorbing heat from its environment. It's now back to the beginning of the cycle. This cycle continues indefinitely.